Welcome to class, ladies and gentlemen. Mr. Eicher here, teaching you even though I'm not here. Just can't get away from my voice. So what we're doing today, Tuesday, week 9, you have a big exam coming up this week. But before that, I thought we'd do a little lesson on tree diagrams. You've probably seen tree diagrams in a previous math, maybe so, maybe not. But this first question, just a little review of conditional probability and a two-way table, so let's check that out. At a middle school, 18% of all students play football and basketball. 32% of all students play football. What is the probability that a student plays basketball given that the student plays football? So let's see if we can organize this information in a two-way table. Let's see. Do I have enough space? I guess we'll find out. So on this side we'll put yes and no. Yes and no. And that'll be if they play basketball. Basketball, question mark? Yes or no? And up here we'll put yes and no. Oops. Yes and no. And that'll be football, question mark, basketball, question mark. So we're told 18% of students do both, so that would be this cell, the yes basketball, yes football, 18%. We'll just imagine that there are exactly 100 and exactly 18 out of 100 play both, so we don't have to deal with the decimals. So we have that, and then we need, let's see, 32% of all students play football. So that would be in our table, that would be, well, let's do like this. So we would have 32 play football. That would be this number down here that I accidentally had a little error there we go. So that would be this number 32 out of 100, our imaginary 100. So that's yes football, 32. That's out in the margin because that's all football players. That's not on the inside. Now we could try to fill in the rest of the blanks, but we're not going to be able to fill them all in. We would have like a 68 here. 32 plus 68 is 100. We'd have what's that, a 14 here. But sadly we can't really figure out like these numbers. We weren't given enough information. Those are question marks. But thankfully, given what the question is, we don't need that information. The question is, what's the probability a student plays basketball given that they play football? So given that they play football, we're only looking at this column right here. Given yes football, I really like this highlighter. Just keep going around a couple times. Given that they play football, well, there are 32 that play football. What's the probability they play basketball? So we're looking at 18 out of 32. So our probability is simply 18 out of 32. So that was a little review of a two-way table. We can organize that with a two-way table. Even though we can't fill in the two-way table, we're still able to answer the question. Alright, let's look at the next question. This question comes from 1997 exam, the very first AP Stats exam. It's question number 26. You'll notice here P equals 55% at the top. That means that only half of the students, a little over half, 55%, excuse me, got this question right. So pause this video, go ahead and read that and see which answer option you would choose. Go ahead and pause the video. Alright, ladies and gentlemen, if you heard that weird flapping sound, that was my puppy shaking and her ears flapping and hitting against her neck or head or something. Maybe you didn't even hear it. Anyway, so let's see. We have a fair coin flipped 10 times and the number of heads is counted. This procedure of 10 coin flips is repeated 100 times and the results are placed in a frequency table. which of the following frequency tables below is most likely to contain the results from these 100 trials. So in flipping a coin 10 times, we would expect roughly 10 coin flips. We'd expect roughly about 5 out of 10 to be heads, right? 50%. And if we repeat this process 100 times, then we would expect maybe 50-ish, 50. Well, let me say it this way. With 100 times, we'd expect the majority, I don't want to say 50, we'd expect the majority to be around 5 heads. So one like this isn't a very good option. That's like you never got heads 0 times, getting 0 heads. That happened 19 times, compared to this getting all 10 out of 10 heads. That would be really uncommon, but this is saying it happened 21 out of 100 times. That's really unlikely. This is really suspicious. To get identical numbers like that, that doesn't seem right. So I'm going to throw out A and B from the running here. Let's check out, come back to C in a second. Let's quickly check out some of these guys. D is kind of weird looking too. D, you have this kind of like pattern here. I'm not sure what would make a pattern like that with flipping a coin. So that doesn't look like a good option. If we look at these two options, C and E, you'll notice that C has like 50%, half of them, we got 5, compared to the one up here, not half of them, so like a little less than half of them had 5 heads. So which one would be the case? Well, I think that this one isn't going to have enough variability compared to one like this up here. I think in flipping a coin 10 times, I wouldn't be too surprised if you had like 8 out of 10. 8 out of 10 heads. That doesn't seem too surprising. This table says it would happen 7% of the time. This says like it never happened to get 8 out of 10. Or like this one, to get 2 heads out of 10. This table says it never happened, but it seems realistic that you could get something like that. So I would choose answer C. Just to better understand the situation, I wrote a little, well, it's not really a program, but if I flip a coin 10 times and I want the replacement, so we get something like that. There's the results of flipping a coin 10 times, and that has 6 heads. If I want to sum that up, this one, so if I did that again, that's 6 out of 10. That's 6 out of 10. That's 5 out of 10. That's 5 out of 10. 2 out. Ooh, see, look, 2 happened. 2 out of 10. Whereas option number E said that it would never happen in 100, or it didn't happen in 100. So, not that you can really program things on the AP exam, but just to maybe better explain what's going on. Here are the results of flipping a coin 10 times, recording the number of heads, and writing the number down. So here are the numbers. If we wanted to see that in a table, here's the table, and you'll notice in this table 5 happened the most, but there is a lot of variability around 5, and we're not too surprised that 8 and 9 happened. You're only flipping it 10 times, so getting 9 out of 10, yeah, it'd be surprising, but it does happen. It's not like it never happens, like 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so all those 0 didn't happen, 0 heads out of 10, and 10 heads out of 10 didn't happen. But that's the type of table that we would expect. Just out of interest, if we made a dot plot out of this, see how quickly I can do this. I like those kind of things. And ylim will do 0 to 100. See if that looks good. Oh, there you go. So there's the dot plot. 1 dot is how many heads you got when you flipped the coin 10 times, counted how many heads out of 10, and then we plotted that number. And oh, look at that shape. Isn't that interesting? Wonder if I did a couple more, maybe 300's too much. Ooh, look at the shape of that graph. How fascinating. But that's not what the question asked, so we should move on. So that was that. Oh, we get another probability question, kind of a review before our main point for today, main topic of tree diagrams. So let's check out this one. Suppose a six-sided blue die has numbered sides 6, 3, 3, 3, 3, 3, and another six-sided red die has sides numbered 5, 5, 5, 2, 2, 2, 2. Both dice are rolled, and the die with the higher number wins. Calculate the probability the blue die will beat the red die. On a situation like this, I would definitely recommend doing the sample space. We have a blue die with these numbers 6, 3, 3, 3, 3, 3. And we have a red die with these numbers 5, 5, 5, 2, 2, 2. And it's whoever wins. So let's see, we'll do B for blue wins and R for red wins. So blue would win on all of these. Blue, 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 blue. Blue wins. Blue would win on a bunch of these down here. Blue would lose on these. So that would be, R. Red wins, red wins, red wins, red wins. Red, 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 red. Uh-oh. Hoping that wouldn't happen. Red, 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 red. But then all of these, excuse me, all of these are going to be B's. So 3 beats 2 and all of these and those. So the probability that blue wins, blue would win in all of these guys. Oh, I'll use my highlighter. All of these guys, blue wins. All of these and these and these. And then I just have to count. We have a total of 36 options in our sample space. And how many do we have there? 6, 6, and 6 is 18 plus 3. So 21 out of 36 would be our probability that the blue die wins, which simplifies to be 7/12. So a little over half the time the blue die wins. That's enough for that. So let's actually look at our content for today, which is about tree diagrams. So let's turn the page. Let's make a tree diagram to represent this situation. Shannon hits the snooze bar on 60% of school days. So tree diagram, we have snooze. She hits the snooze bar or not. And on this branch, we put the 0.6. On this branch would be the complement, so that would be 1 minus 0.6 is 0.4. And tree diagrams are helpful when we have things that are chronological, like she has to hit the snooze bar chronologically first before she makes it to school. Like you have to get up before you make it to school. You have to get out of bed. So we have if she doesn't hit the snooze bar, so that's down here. If she doesn't hit the snooze bar, she's either late or not. And there's a 90% chance that she makes it to class on time, so that would be not being late. And then the complement of that is 0.1. If she does hit the snooze bar, late or not. However, if she hits the snooze bar, so we're at the top now, there's only a 70% chance that she makes it to class on time. 70. And the complement of that is 30. And then what we can do is we can multiply these branches. 0.6 times 0.3 is 0.18. 0.6 times 0.7 is 0.42. 0.4 times 0.1 is 0.04. And 0.4 times 0.9 is 0.36. A couple of things to notice about these numbers. You can check your work here. They should all add up to 1, and they do. Also, these two bottom ones should add up to this original bottom branch. And then these two top numbers should add up to this top branch, and they do. So we can use tree diagrams to answer probability questions. Most likely on the AP exam, you would not be asked to make a tree diagram. You'd just be given the question on B or C. So you have to get a sense of when a tree diagram or a two-way table or some other approach, when it might be helpful in a certain situation. So I'm going to X out of here and lose my beautiful tree diagram, but that's okay. So, on a randomly chosen day, what is the probability that Shannon is late? So, originally we had something like this. This was snooze or not. And we had two branches that said late. It was this top one and then this third one down. So when we're asked this, we really want to know what's the probability of this and what's the probability of that. And I believe we had those numbers written above. There's an 18% chance that she hits snooze and is late. And there's a 4% chance that she doesn't hit snooze and is late. So our answer, our probability for being late, that would be the sum of these two, add those two, and you get 0.22. So our probability that she is late for class is 22% chance. Suppose that Shannon is late. What is the probability that she hit the snooze? So notice this statement right here. Get rid of that for now. This statement, suppose that Shannon is late for school. This indicates to us that it's a conditional probability. So as a conditional probability, we want the probability, given that she's late, we want the probability that she hit the snooze given that she's late. And that would be calculating. Our denominator is now that given part, that condition, the probability she's late. The numerator is the probability that she hit snooze and is late. Some notation there. So what's the probability she's late? Well, we calculated that up here, 0.22. And what's the probability she hit snooze and is late, this numerator? Well, I believe that that was this number from the tree diagram, hitting snooze and is late, 0.18. The neat thing about conditional probabilities with tree diagrams is whatever the denominator is, the denominator tells you, it's a 50-50 chance, people, it tells you what the numerator is going to be. That denominator had the 18 and the 4, and the numerator, the one that we wanted, was that she hit the snooze button, is the 18. So this denominator always has the number that you're going to use for the numerator. You just have to figure out which one they're asking for. So if you're using like 42 or 36 from earlier on the numerator, you're way off base. It has to be one of these two numbers. You can also represent this situation with a two-way table. I'm going to write that at the top. Get rid of this. Move up here. And see if you can set up the two-way table, not maybe fill in the numbers, but see if you could label like what's at the top, what words, and what's on the left side, and what words. So pause this video and see if you could do that. Alright, so I have my snooze variable, yes or no. And I have my late variable, yes or no. So we'll start with the first comment. 60% of days she hits the snooze button. That would go way out here. So that's for the yes snooze, all the way in the margin. And then by default, I know that's 40. Again, I'm working with an imaginary 100 people, exactly 100. And now the tricky part is on the inside. We have this 90% probability that if she doesn't hit the snooze, so that's down here, she doesn't hit the snooze, there's a 90% chance. So how many days would that be? You have to do 90% of the 40. 90% of 40. And that would be 36 with a leftover 4. So again, that 36 came from, it's 90% out of 40 days. So how many days is that? 90% of 40 is 36. And then this probability that we have 70%, that would be 70% of the 60 days. 70% of 60. So 70 times 60 is 42. And then 60 minus 42 is 18. We can add down here, and add down here. And then we have our two-way table. And you can use this two-way table to answer questions like, what's the probability that she's late? Probability she's late is this number, 22. And then what's the probability given that she's late? What's the probability that she hits snooze? That would be 18 out of 22. Given she's late, probability she hit yes, snooze. So you can use two-way tables to answer questions like these. I do want to point out, and also just so I can use this circle option. Ta-da! These numbers, ta-da! Sorry, I need to work on my timing. These numbers are all the numbers that we had on our branches. Remember, we had the 0.18 on a branch, we had 0.04 on a branch, we had 0.42 on a branch, and we had 0.36 on a branch. All those numbers match what our tree diagram had. Let's now look at another tree diagram. Turn the page. Alright, so we have false positives and false negatives. False positive, false negative. So what a false positive is in the medical field is the test says positive, but it's wrong. So I don't know, that's like you walking into class and I say, hey, great job on your test, you got an A, but that's wrong. Ouch. Sorrow and sadness. But in the medical field, that could actually be in some ways a good thing. Like the test says you have cancer, but the test was wrong, and then you can breathe a sigh of relief. Of course, you might be really stressed while you wait to see if the test was wrong. But that's a false positive. So the positive is what the test says, and the false part says that the test was wrong. False negative is kind of the same thing. The test says negative. The test says negative. You do not have cancer, but it's wrong. That would be very disappointing and a problem too if you're going around thinking you don't have cancer, but in reality you do, and it goes undetected. There's some words for these that aren't on the AP statistics exam. I think this one is called, maybe AP Psych people know this, but this one is called, I think, sensitivity. And this one's called specificity. That is a word, specificity. Not that you need to know those, but sensitivity is the determination that the test says positive and it's correct. Anyway, I probably shouldn't even be talking about it. I'll just get rid of that. Forget I even said that. Okay, so let's answer this. Many employers require prospective employees to take a drug test. I had to do that to join this school. A positive result on this test indicates that prospective employees use illegal drugs. However, not all people who test positive actually use drugs. Suppose there's a 4%. Suppose that 4% of prospective employees use drugs. The false positive rate is 5%, and the false negative rate is 10%. What percent of prospective employees will test positive? This is a good example on the AP exam. They're not telling you to make a tree diagram, but let's make a tree diagram. Again, chronologically, you would have to either use drugs or not before you're tested for the drugs. Like, you would have to be either a drug user or not a drug user prior to even like getting this job and having to take a drug test. So this is a good candidate for a two-way table. So, for a tree diagram. So either you use drugs or you don't. So this says, let's imagine that 4%. So we'll draw that 4% use drugs and 96% don't. And now these branches are relating the positive or negative result on the test, positive or negative. We just have to figure out which one is which. So we have a false positive rate of 5%. So a false positive would be which one of these two positives here, this one or this one, the test says positive, which one is false. And positive means that you use drugs. So this one up here, that one's correct. You use drugs and it says you use drugs. That's accurate. That's not a problem. Well, it might be a problem in other ways. But this one down here would be our 5%. This is you don't use drugs, but the test was wrong and said you do. And then this would be 95%. And then the false negative rate would be this one right here. It says you don't use drugs, but you really do use drugs. 90%. Now, we could multiply all of these out. If I had a calculator, I would do that, but I don't, so I won't. We're trying to answer this question, what percent will test positive? Well, the percent that tests positive would be this branch, test positive, and this branch, test positive. So we need to go 0.04 times 0.9 plus 0.96 times 0.05. And then we add those, and we would get our answer. Calculating that, you can check my work, but I got 0.084. So that is the probability someone will test positive. So there's 8% chance that there will be a positive test. What percent of prospective employees who test positive will actually use illegal drugs? So notice what percent of just this particular group. This is a conditional probability. So we would like, what's the probability that they use drugs given they test positive? That would be, the denominator is the probability they test positive. We just had that earlier, so that was 0.084. And the probability they use and test positive. Probability they use and test positive was, let's see, 0.06, if I can remember the numbers, times the probability they test positive. What was that number? So we had use, not use. Oh, I think that was 10%. Is that right? You would think I could just scroll up, but I really can't without losing all my hard work. So this was the use. This was the positive one. And the the negative was 10%, right? The false negative. So that would be a 90. And then dividing those, we would get our conditional probability, the percent who actually use illegal drugs, given that they test positive. So that was 0.06 times 0.9, I believe, divided by 0.084. And I got 64%. 0.64 probability. So given they test positive, what's the probability they actually use illegal drugs? There's a 64% chance. That might seem kind of strange to you. Like if there's a positive test, it's not like 100% that you use drugs. It's probably like more likely that it's a false positive than that you actually use drugs. But that would be the probability that we're trying to calculate there. So those are two examples of tree diagrams. I would like you and your neighbor to work on 1997 number 3. I can post the solution. It's actually available online if you just do AP Stats 1997 number 3. But maybe at the end of this video I will post the solution. But take about, I don't know, 10 minutes or so, see if you can answer these questions. Thank you. All right, hopefully you did well, you and your neighbor. Let's check out this answer, sample number 1. Here's a student setting it all up. And see if you made a tree diagram. The answer you should get for A is 0.06894 as your probability. And for letter B, conditional probability, should get 0.71076. That's what it looked like if you did tree diagrams. Here's the tree diagram for you, if you want to check that out. But also, you could have used a two-way table. You can see that up here on the right. If you set up a two-way table, just have to multiply stuff to get those inner cells. That was it. So that's an example of AP Stats, kind of an old one, but an AP Stats question using tree diagrams. Hope you enjoyed this video. Enjoy the rest of your day. Thank you.